Good afternoon, everyone. Thank you all for joining us for today's Net Zero Week webinar. The title is Fusion Energy and the Role of Standards. It's great to see so many of you here today, and I'm delighted to welcome you to what promises to be a dynamic and hopefully informative session. We've assembled an outstanding panel of speakers, and I'm confident today's discussion will offer valuable insights into one of the most critical areas of our energy future. Before we dive in, let me briefly allow me to set the scene and explain what Net Zero Week is. Net Zero Week is a cross-sector initiative led by the BSI Knowledge Solutions team, bringing together experts from our key sectors. That includes transport, ESG, healthcare, digital, built environment, food, and obviously energy. Our focus today is on energy and specifically nuclear power and nuclear fusion, two technologies that are not only central to the UK's energy strategy, but increasingly vital to our global net zero ambitions. So let's start with the big picture. The UK was the first country to legally commit to net zero by 2050. That means eliminating nearly all greenhouse gas emissions across the economy and doing so in a way that's secure, affordable and resilient. But the clock is ticking. The Labour government has shown real ambition and raised the bar. It's pledging to decarbonise the UK power grid by 95% by 2030. Which is only 4.5 years away, and ultimately aiming to be a net zero economy by 2050. To meet these targets, we need a dependable mix of low carbon energy sources. Wind and solar will play a major role, but they are intermittent. We also need low carbon power that can operate 24/7, regardless of weather or time of the day. And that's really where nuclear comes in, and it's currently a very exciting time for nuclear. Last week, the UK and US governments signed the Atlantic Partnership for Advanced Nuclear Energy, marking a new era of collaboration. The deal includes plans to build up to 12 advanced modular reactors capable of powering 1.5 million homes and creating 2,500 jobs. It also includes an £11 billion initiative to develop data centers powered by small modular reactors, or SMRs, to support the energy demands of AI and the digital infrastructure. Now, these reactors are fast to deploy, scalable, and ideal for grid balancing. They also provide the kind of clean baseload power that's essential for a decarbonised grid. And they're attracting serious investment from governments, industry and tech giants alike. But nuclear innovation doesn't stop at fission. The UK is also leading the charge on fusion energy, a technology that could redefine our energy future. Fusion offers the promise of abundant, zero carbon power without long-lived radioactive waste. And this week, the UK became the first country in the world to introduce fusion-specific planning rules, streamlining approvals and accelerating deployment. The STEP programme is at the heart of this effort, and it aims to build a commercial fusion power plant by 2040 and really creating a hub of clean energy innovation. With a £2.5 billion commitment to fusion R&D, the UK aims to become a global leader and a global player in this transformative field. These developments are not just exciting, but they're essential. Meeting net zero by 2050 requires rapid deployment of clean and low carbon technologies with long-term solutions that are scalable, secure, and sustainable. So as we begin today's conversations, let's keep in mind the scale of the challenge and the opportunity. Net zero is not just a policy target, it's a natural imperative or a national imperative, and nuclear energy in all its form is a cornerstone of this vision. So in order to lead this conversation, we'll have a panel of experts who I will introduce briefly while I'll run through some of the agenda. Okay, here we got a panel introduction. Sorry, I couldn't see the screen there. So let me introduce the panel that we have for you today. We've got Dr. Isabel Houghton, who's the Chief Engineer and Fellow in Advanced Nuclear Technologies at AtkinsRéalis Nuclear. Isabel is the Chair of BSI's NCE1 Nuclear Coordination Committee, which coordinates nuclear-related activities across various BSI committees. It identifies and addresses gaps in nuclear standards portfolio and provides expert advice on developing new standards relevant to nuclear technologies, including emerging areas like fusion. Outside of BSI, Isabel is an award-winning Chief Engineer and Fellow in Advanced Nuclear Technologies at AtkinsRéalis. She has a 17-year track record of delivering complex technical projects in both fission and fusion. Isabel specializes in leading multidisciplinary teams to deliver innovative solutions to some of the most significant challenges in low carbon energy, including the development of both Gen 4 fission and fusion power technologies, as well as specialist expertise in external hazards. Dr. Mutaz Bashir is a fusion systems and components leader at the UK Atomic Energy Agency. Mutaz is the chair of the working group on fusion in vessel components in the American Society of Mechanical Engineers, Boiler and Pressure Vessels Code, under Section 3 of the Nuclear Code, Division 4 on fusion energy devices. His area of expertise in the past 20 years has been on the development of advanced methods for the structural integrity assessments of components in challenging environments, such as high temperature applications, with a particular focus on the implementation of finite elements, modeling for design assessment. Mutaz was also leading the development of the demo fusion plant in components design rules between 2018 and 2022. He is currently working on establishing a fusion industry-wide group via the ASME platform to coordinate efforts to address the challenges facing the fusion industry in the design of in-vessel components. And finally, we've got Dr. Amanda Neatveld, Head of Business Development at Digilab. Amanda is a Head of Business Development at Digilab, where she leads strategic growth and partnerships. She has over a decade of experience in public and private partnerships, and she has a proven track record of driving organizational expansion and fostering impactful relationships centered around technology development and adoption. At Digilab, she focuses on bringing trustworthy, explainable AI to market in safety-critical sectors where uncertainty matters and trust is paramount. She led Digilab's rapid expansion into the fusion sector and works closely with public and private organizations to enable and accelerate AI adoption across a range of industries, from advanced energy to environmental monitoring and healthcare. She enjoys working in the interdisciplinary teams and is passionate about ensuring that human context and needs are embedded in the technology creation and adoption journey. Now, before I hand over to our speakers, allow me to provide a very brief overview of BSI and our role as the national standards body in this space. Next slide, please. So, to give an overview, we are the UK's national standards body. Most countries have one national standards body as their standards body, and we're the one for the UK. We are independent and apolitical, but operate in the national interest. So we have an MOU with government. Interestingly, we are both independent from government and independent from industry. We are a not-for-profit, or particularly as our chief exec likes to call it, a profit-for-purpose organization. And what that means is that we do generate profits, but those profits don't go to external stakeholders. They stay within the company to help deliver on our purpose, which is supporting with national and international standardization needs. All standards that we create go through a stakeholder-led process that comes from consensus and consultation. And through this consensus and consultation process is where standards get their legitimacy and reputation from. Standards have the potential to deliver and support on government policy objectives, and particularly in spaces like the energy transition, I think they work very closely to support policy objectives. All decisions that we make are always in this context. Next slide, please. Now, as I mentioned, we are the UK's national standards body, but we are also members of the International Standards Fora. That includes CEN and CENELEC at the European level, IEC, ITU, ETSI, and ISO. I think it says it's 164 national standards body members globally. I think it might be more now, 170, but that provides a global infrastructure for standardization, and we provide the UK perspective into international standards making. Next slide, please. Now, as I mentioned, it is an exciting time for nuclear, and the UK is making significant commitments. So just to highlight the investment case, 410 million has been committed earlier this year to boost the fusion energy sector, and over 2.5 billion has been assigned in the spending review to fusion R&D over 5 years. From policy and programs, government has committed to being the first country to develop fusion-specific planning rules, and fusion to be introduced in the nationally significant infrastructure project regime, putting fusion energy projects on the same footing as other clean energy tech. The STEP prototype is aimed at demonstrating commercial viability, and the outcome of consultation on the future national policy statements is expected in March 2026. Next slide, please. So what do we do in the area of nuclear standardization? As the national standards body, we facilitate 4 technical committees overseeing standardization for nuclear energy, and this ensures that the UK industry maintains a strong voice in the development of European and international standardization. We've recently set up NCE1, the Nuclear Coordination Committee, which was established earlier this year to provide strategic direction for national standards efforts and identified fusion as a key strategic priority. As mentioned earlier, Dr. Isabel Houghton, who we'll hear from in a little bit, is the chair of this technical committee. BSI also takes part in the Nuclear Standards Forum, which is overseen by the Department for Energy Security and Net Zero, and this platform for industry experts and regulators focuses on collaboratively developing and maintaining rigorous safety and quality standards in the nuclear sector. Next slide, please. So here we see the infographic of the technical committees that we have and how they feed into the international standards arena. Next slide, please. And as I mentioned, NCE1 is on National Nuclear Coordination Committee, not a technical committee, but a nuclear coordination committee. It coordinates across. And when we look at fusion in particular, there's NCE2, radiation protection and measurement, and NCE3, reactor technology, which looks at fusion technology. And all of these technical committees provide our input into national standards making for the nuclear industry. I think that's sort of enough for me and standards as a high-level overview. So I want to hand over to our first speaker. And our first speaker is Dr. Isabel Houghton, Chief Engineer and Fellow in the Advanced Nuclear Technologies at AtkinsRéalis Nuclear. Isabel, can I ask you to turn your camera on, please? There you are.
Thanks, Seb. Thank you for that.
Hand over to you there.
Thank you. So as Seb's mentioned, I'm Isabel Houghton. I work for AtkinsRéalis in our nuclear business. I've been working for Atkins now for a while, and we've been delivering fusion projects for over 15 years across the world and across a range of different disciplines. So from civils and materials, project management and safety, mechanical and process, to name but a few. I just wanted to give you a little overview of some fusion projects that we've been involved in. I've got a picture, big picture on the left-hand side of the inside of ITER that was taken by one of my colleagues down in the south of France only a couple of weeks ago. As Seb's mentioned, I'm also the chair of the BSI NCE1 committee, and as he's mentioned, we're a coordination committee and we're operating as a horizontal systems committee. We don't develop standards, but we coordinate nuclear-related information and activities across BSI technical committees. Seb's already mentioned that fusion is one of our strategic priorities within NCE1. Our other strategic priorities are the use of AI within nuclear, so both within fission and fusion, and also decommissioning, because that whole life cycle picture is really important for both fusion and fission. At the moment, NCE3, for example, is engaged in a number of work proposals addressing fusion technologies. Those have been typically proposed by our international colleagues, highlighting how the fusion standards landscape is very much an international landscape. And I'll come on to talk about that in a bit later. The role of NCE1 and our supporting committees is not about standardizing specific technologies or standardizing specific fusion technologies. We don't want to stifle innovation. We don't want to box in creativity. Fusion is still very immature as a technology, and we're looking at how we can best support the commercialization of fusion power to meet those net zero targets that Seb's already talked about. So before we go any further, I thought it would be worth us just thinking a little bit about what is fusion, and just set the scene. What is fusion? And think about why fusion is so interesting right now. So fusion is the process where two light atomic nuclei collide and they combine to form a single heavier nucleus, and that releases immense amounts of energy. It's the same process that powers the sun, which is shining beautifully where I am today, and the other stars around us. Scientists have been working to harness fusion to generate clean energy for as long as I can remember, from back when I went on a school trip to JET as a sixth former. Before then, trying to generate clean energy is going to involve heating hydrogen fuels, typically deuterium, tritium, to extreme temperatures to create a plasma. And then the technical challenge is to contain this super hot plasma long enough for the fusion reactions to occur and produce usable energy. I'm not going to go into any more detail about fusion now, but if you're interested, I would really recommend checking out UKAEA's YouTube channel, which has got a series of really, really good introductory videos on fusion. So that's highly recommend that. Why is fusion a hot topic right now? Well, we've been looking at fusion for over 50 years. But the crucial point about where we are today is that fusion is moving from research programs, so for example, JET, the Joint European Torus here in the UK, is moving from those research programs to the first commercial applications. So for example, STEP, the Spherical Tokamak program that UKA is running, or equally other types of fusion machines. So I've got a picture on the left there of Proxima Fusion Stellarator technology. Slightly different to the Spherical Tokamak that STEP is planning to use, but still another example of how fusion technology is being driven towards commercial fusion power. A recent Fusion Industry Association report attributed over $7 billion of global investment into fusion by 2025. And that to me really illustrates how the promise of commercial fusion power is attracting significant investment. So for the rest of my time with you today, I want to talk about how standards, the standards that we work on here at BSI, can support that development of commercial fusion energy. And to talk through that question, I'm going to talk through three main themes. I'm going to talk about commercialization, I'm going to talk about safety, and I'm going to talk about regulation. So in terms of commercialization, to make something commercially viable, it needs to be supported by the supply chain. And we know that in the UK, one of the ambitions for the STEP program is to kickstart a UK fusion supply chain. I want to go a bit back in time to share an example of how standards can support the supply chain and illustrate how having these standards is really helpful to making sure that our supply chains have the abilities to deliver what the fusion industry needs. So I've got a picture up on the screen here of the Whitworth thread. So this was the world's first national screw thread, and it was devised and specified back in 1841, back in the 19th century. So until then, the only standardization around screw threads was very much ad hoc, localized patches, making it very difficult to share designs from one workshop to another. However, the Whitworth thread was beautifully timed. So during the Crimean War, the Royal Navy needed a lot of gunboats and they needed a lot of engines to power those gunboats. The supply chain was able to deliver 90 engines in 90 days for these gunboats because the components in the design were standardized. They were using, for example, the Whitworth threads. And what that meant was that the supply chain was set up to deliver those standards. So if we're talking about fusion, we need the fusion supply chain to have similar standards that can be applied across components to enable rapid turnaround of production, to make sure that we're minimizing delays, we're facilitating rapid manufacture of components to meet the needs of the supply chain. However, it's worth reflecting now that standardization of screw threads only worked at that point because the technology was mature. Screw threads were all understood, people knew how to make them. The key was to standardize what was required for each and every one of them. So I'm going to move on now and talk about safety. So without safety, nobody has a commercial proposition. I mean, no one is going to invest in a fusion power plant that isn't considered safe. It won't get a license. And the example I want to share here is that of the containment barrier at ITER. ITER is, for those who don't know, ITER is another research reactor that's being built in the south of France, but it's the biggest fusion machine that has been constructed to date. In France, fusion installations are regulated by ASN, the French nuclear regulator. That's a different situation to what we have here in the UK. Here in the UK, fusion programs are not regulated by the ONR, the Office for Nuclear Regulation. They're regulated by the Environment Agency and the HSE. So there's a difference there about regulation, and I'm going to come back to that in a couple of minutes. But coming back to ITER, here we've got a picture of two gentlemen doing some laser welding on the containment barrier. They are attaching spigots to the outside of that barrier, so the key items of equipment can be attached to the outside of the containment barrier. So the containment barrier is a really, really important component within the design of ITER. And it's critical that its integrity is maintained. But because we understand the requirements of containment barriers from the nuclear fission industry, there are already existing standards that can be applied to welding on that outer containment, on that first containment barrier. So within the ITER program, within the regulation by ASN, the integrity of that first confinement barrier at ITER, its integrity is ensured by observation of procedures that are controlled by nuclear safety, quality, and third-party nuclear inspectors. This is all covered by existing standards. Existing standards have been mapped from fission to fusion to avoid rework, and it's helping to avoid error traps. And it also means that we've got read across from the different industries, and that's another key part of the supply chain, making sure that we have access to staff who understand what those standards are already from previous experience on different programs, who can then bring that and apply that within the fusion industry, and in this case to weld spigots onto the first containment barrier at ITER. So I've already alluded to regulation, and that's going to be the final thing that I want to talk about today. I've already mentioned that in France, the fusion is regulated by ASN, whereas here in the UK, fusion is regulated by the Environment Agency and HSE. Rather than talk about fusion regulation, I want to give an example about the importance of commonality across regulators, some of the challenges that we see by looking at an example from the fission industry. So I want to compare Flamanville on the left and Hinkley Point C on the right. So Flamanville, French reactor, EPR design, European pressurized reactor design, that is now being implemented here in the UK at Hinkley Point C and then extended further at Sizewell C. So the ambition was that the deployment of the EPR design in the UK would be very straightforward because it had already been developed and demonstrated in France. However, what we've seen in that programme is that there have been significant changes to the Hinkley Point C design that have been needed as a result of the differences in the regulatory regimes between France and the UK. So for fusion, where we have fusion-specific aspects, the earlier we can drive commonality between different nations interested in fusion, interested in deploying fusion, the better. And this needs to cover things from design to specification of materials and everything in between. This approach of collaborating internationally and having consensus internationally will really work for the UK if we can be at the forefront of deployment, as we can replicate what we've shown a successful deployment in the UK into other countries. And that will help us use our own supply chain that we've developed and we've supported through the use of standards, through the use of existing standards and transferable skills to develop that UK supply chain to lead the rest of the world. And this supports part of one of the aims of the STEP programme, which is to create a fusion industry here in the UK. What we need to avoid is developing a system or a component in one country that we then can't deploy in another country without significant investment in additional qualification or design changes to meet local regulatory requirements. So in my view, fusion really needs to push for greater commonality, allowing suppliers to offer their products to global programs to avoid incurring additional costs or schedule delays, which will only challenge the commercial model. So in terms of the BSI position or the NCE1 position on this, I've talked about how standards in general can support commercial fusion energy. In terms of what specific standards we need, specific fusion standards that we need, our view in NCE1 is that it is too early in terms of technical maturity of the technology to pursue standardization in fusion. And at this stage, any standards that we're producing within BSI, within ISO, they should be enabling technologies. They should be embracing the fact that we've got a lot of innovation to do around fusion technology, and we don't want to be restrictive around future technologies. Some of the recent fusion standards raised with NCE2 and NCE3 illustrate the current trend of standards proposals which focus on particular technologies or really narrowly defined solutions, and that's not supportive of this commercial fusion model that we're working towards, because this approach could hamper development, particularly in countries where standards are very prescriptive. So in my view, generation of these prescriptive standards would really challenge our position in the UK as a world leader in fusion technology. So where do we go next for fusion tech standards? In my view, we need to use existing standards where possible, where that's appropriate. So whether that's screw threads, I'm not advocating Whitworth threads necessarily, or safety or welding standards. Using those existing standards where possible and appropriate will give clarity to the supply chain, and it will also provide the people within the supply chain with the confidence that they have the skills to transfer from one industry into the fusion industry. We need to capture the current fusion specific best practice from across the world, from across the different programs that are going on. And we need to share that understanding through recommended practices, design guides, technical notes. We need to share that. It gives us a great shared working base to start from and to develop standards in future, but we don't need to standardize just yet. And finally, NCE1 really supports the creation of the fusion specific ISO working group under ISO TC 85 SC6. So in terms of where next for fusion standards, BSI is ideally placed with support from its UK experts it's able to draw on to lead development of the standards that we're going to need for fusion to realise the UK's ambition to become a global leader in commercial fusion energy. Thank you very much.
Brilliant, thank you very much, Isabel. Really interesting. The screw threads example is one that, yeah, it's sort of, I don't know about that one specifically, but I like those sort of examples. Again, it shows you what that does, standardization. The one that I came across was when we standardized shipping containers on ISO 668 and how that provided commercial growth or rapid growth in both shipping, but also in trade. The quote that I like to pick out, which I thought really stood out for me, was "Without safety, there is no commercial proposition." I think that's something that we sometimes forget. So yeah, there's a lot of food for thought. I think that was really insightful. I'd now like to hand over to Mumtaz Bashir, who's the Fusion System and Components Leader at the UK AEA. Over to you, Mumtaz.
Thank you, Sebastian. Good afternoon, all. My name is Mumtaz Bashir, and I'm the Group Leader for Fusion Systems and Components within UKAEA's Office of Chief Engineer. And I'm also the Chair for the Working Group on In-Vessel Components as part of the ASME Boiler and Pressure Vessel Code, Section 3 on nuclear installations. And my topic today is really aiming to highlight some of the key considerations for the development of codes and standards for in-vessel components. That's fusion in-vessel components. In terms of what I'll be going through, a brief introduction to fusion energy and highlighting some of its key benefits. I will also say a few words on commercial fusion and the leap the technology would have to make in order to reach commercialization. I'll also say brief words on the current state of fusion codes and standards, and finally use in-vessel components as example of highlighting some of the challenges the technology would be facing, and close finally with some remarks. We all know that fusion is the source of energy that heats the sun. As been mentioned, you'll never hear this enough today. And in a fusion power plant, this is replicated in the fusion chamber by using an external heat source. to heat up the light nuclei. In the example on the right, on the image on the right-hand side, is tritium and deuterium, and these are heated to over 100 million degrees Celsius to plasma state, triggering the fusion process. Energy is released from this fusion process in a form of thermal energy, and it's also accompanied with high energy neutrons, which consequently impart its energy on the surrounding components within the vicinity of the fusion chamber. And helium is also released from this reaction. The image at the bottom of the slide illustrates a fusion power plant in which the energy release from the fusion process will be harvested or used to power up a steam generator and feed into the electric power grid. Of course, there are many benefits to fusion, but the one I would like to pick first for this net zero event is that fusion is a low carbon form of energy with a low land footprint. It's also, of course, safe. Hence, the fusion process is readily and safely controllable, and it's also reliable source of energy, as it does not depend on seasonal variations. And the sustainability of fusion lies in the potentially abundance of fuel in seas and earth crust. And last but not least, it's an efficient energy and provides the most power dense process on Earth. Now, to say a few things about commercial fusion, and having highlighted all of these brilliant benefits, it nevertheless involves highly complex and highly sophisticated engineering systems, which are all at the forefront of the key engineering challenges facing the transition of fusion to commercialization. And just looking at the three key parameters for a fusion process, perhaps we'll give an example and a flavor of these systems. So the first fusion parameter is the plasma temperature, which is reliant on the heating system. And of course, the plasma temperature is very critical to ensuring that the fusion process is occurring at a sufficient rate. And hence the heating systems are of critical importance for the fusion process. An example of such heating systems is the neutral beam injection and radio frequency heating systems. The second parameter is plasma density, which relies on precise supply of fuel to the fusion process and effective removal of impurities from the fusion chamber, and hence historically linked to fuel and exhaust systems. The last or third parameter is plasma confinement time, which is necessary to ensure that the fusion process continues for longer durations. And in the case of the tokamak, which is a concept it's considered here in the UK and in STEP in particular, uses magnetic confinement, and hence magnetic systems are very critical indeed for the fusion process. Looking at the image at the bottom here, it illustrates the challenges and the leap in terms of advancement required for all of these systems and many other systems that are not listed here in order for us to head towards commercialization. So if we look at JET, for example, and which is the Joint European Torus here in the UK, the Q factor, which is a measure of the amount of energy release from the fusion process versus the energy input to trigger the fusion process and maintain it, is achieved circa 0.6 Q factor. ITER, the International Thermonuclear Experimental Reactor in France, in the south of France, is aiming to achieve a Q factor of 10, and a future of the commercial fusion is to aim for a Q factor of 25 and possibly more. So this gives an indication of the technological challenges ahead. To say a few things about fusion codes and standard and the current state. In recent years, with many initiatives, with a lot of the standards and the codes are in draft form or work in progress, but as of yet, there are none that are in a comprehensive, usable form for fusion technology, apart from a couple of subsections in the Japanese code, the GSME code, and the French RCCMRX code. Nevertheless, and just compared to a few years ago, with the substantial increase in private and public sectors fusion investment, this played a very positive role in increasing the momentum in this area. And this is evident by the dynamic currently being observed from technical working groups to committees within many of the standard development organizations, especially within BSI, ISO, and the American Society of Mechanical Engineers, ASME, Boiler and Pressure Vessel Code. And I'd like to take this opportunity to really call on experts, fusion experts in all fusion technologies, to start and aim to cluster around these standard development organizations to proactively help and support with the development of these codes and standards. And indeed, fusion in its current phase, transitioning from research into commercialization, in itself is in very much need of codes and standards, because codes and standards offer a strong technical standing as well as a strong regulatory standing. In terms of technical standing, of course, it ensures that relevant first engineering principles are applied, and ensures that this is reinforced by operational experiences, either from small scale or large scale fusion machines. And it brings about subject matter experts to review and vet and accept these technical principles. And finally, it allows for covering a much larger scope that covers through the component and system throughout their life cycle, from material specification all the way through to decommissioning. And of course, its regulatory standing also accelerates the regulatory processes and procedures, in addition to it allowing for consideration for any regional regulatory requirements, as well as ensuring that the technical content of these standards is precisely checked for it to be meeting the regulatory and the safety objectives. Now, having said all of that, it's not. We are all aware that that the challenges lies ahead is very complex and poses a lot of challenges. And in this example here, I'd like to use some of the considerations. It's not comprehensive, but it gives an indication of the magnitude of challenges and effort that will have to be put into the development of fusion codes and standards. I'll use in-vessel components in this example here. Now, in-vessel components, technically, they refer to all components enclosed in a vacuum vessel in the case of this tokamak machine here. But in practical terms, and given the engineering challenges, it typically tends to be referring to components within the vicinity of the fusion chamber. These are categorized as plasma-facing components. as well as components very close to this fusion chamber. And by contrast, these are categorized as non-plasma facing components. Now, these components are maybe there for functional purposes, structural, diagnostic component or instrumentations, amongst many other applications. And the message here is really that such categorization is really important from standard development point of view, because it distinguishes that each of these components, despite the fact all being inside the vessel, they maybe have different requirements set against each of these, and it needs to be considered as such. Now, just going a little bit into details with the in-vessel components and indicating the three main components that are posing most of the challenges across all of fusion concepts are the first wall, breather blanket, and diverter components. Now, the first wall is the component that covers the largest area within the vicinity of the fusion chamber, and is considered as the armor directly facing the fusion plasma, and hence receiving the largest amount of thermal and high neutron fluxes, and is the key protection component in the fusion machine. Now, the breather blanket, on the other hand, it functions for fuel breathing, and which is necessary to keeping the fusion process continuing. And it also, in some of the concepts, it facilitates neutron multiplication, and it typically consists of the breathing material is contained in compartment-like structures within the main support structure of the breather blanket, with cooling channels running through it. The diverter component, which is at the lower part of the machine, within the vicinity of the fusion chamber, function as an exhaust system to remove impurities from the fusion chamber, also necessary for the continuation of the fusion process. And it typically consists of a target structure that comes in contact with the fusion plasma, and a main support structure, and cooling channels as well. The first wall is the component that harvests the primary heat source that is used for powering up the steam generators in a fusion power plant, where breather blanket and diverter also absorbs energy, but is considered as a secondary source for powering up the steam generator. Now, having mentioned all of these structural and functional features for in-vessel components, these will need to be considered in conjunction with the loads and environment generated inside the fusion chamber when developing code and standard for in-vessel components. And as illustrated in the image at the bottom of the slide, closer to the plasma, you have very high heat flux and elevated temperatures that generate very high thermal gradients as you move away from the fusion chamber. And also there is high energy neutron flux, which also propagates at a gradient as you move away from the fusion chamber. Also, there are interactions with the plasma. Some of the in-vessel components interact with the plasma locally, and this needs to be considered. And there will be forces from the plasma during some plasma scenarios. Most critically is plasma disruptions. There is also absorption of fuel or tritium and helium for the materials inside these components, which also need to be considered. And finally, there is electromagnetic loads, of course, in the tokamak concept, although this comes from the magnet system outside the vicinity of the vacuum vessel, but they also huge forces that would need to be considered when developing standards for in-vessel components. Now, all of these load and environment conditions would mean that that very complex failure modes will have to be considered when assessing designs, especially with the multi-material concepts with hugely varying properties that are being considered for these in-vessel components, such as the example shown here to the right for a diverter target, where tungsten or tungsten alloys are used as an armor or protection structure, and that is joined to a copper or a copper-based alloy, or in some cases stainless, in some concepts stainless steel, as cooling channels. So all of these multi-varying concepts would require consideration of very complex failure modes, both ductile and brittle for the respective materials. The service conditions in terms of temperature and neutron fluence will also need to be considered. For example, in the case of elevated temperature, that brings about new other failure modes that need to be accounted for, such as creep, and with the neutron fluence, depending on the level from low to high, it induces embrittlement into the material that could lead to partial or holistic embrittlement, and that also need to be considered. And also another considerations for neutron fluence is that it tends to change the temperature at which the material transition between ductile and brittle state, which is indeed very complex. And of course, there are many other considerations. I've put in here melting. There is also the so-called plasma erosion, and many more that would need to be considered in the development of standards. And I think mainly the approach of the first generation of prototype fusion power plant is to have a very carefully planned monitoring and measurement program to be able to identify all of the key considerations to be taken for assessing in-vessel components. This also entails that the basis for design assessments will have to be also carefully considered with all of this material variability and transitioning nature due to neutron fluence. It brings about a very special case for setting basis for design assessments by carefully considering the design throughout its service life and all the stages, right from the beginning to the end of service life as well in between. And this also entails that design methods, for example, the widely used design by analysis method needs huge amount of advancement and extension such that it is fit for purpose, and also looking at route for where design by experiment can also be included. So I hope these last few slides on in-vessel components just help to clarify or give you an idea of the magnitude of the challenges ahead, which need to be considered for the development of fusion standards, and in this case for the in-vessel components. And indeed, there are other similar challenges in all other components and systems. I'd like to finally close with few remarks in that commercial fusion in both private and public sectors is now really taking big or very big strides. But the good thing is that many of the key engineering challenges are largely common amongst all concepts, and this is really good to set good ground for collaboration and coordination, which is really critical for realizing these challenges. And I would hugely encourage and endorse that and highlight that standard development organizations really are excellent platforms for development, and they've been long calling for Fusion experts to support this. And I would say now is the time, or maybe sort of our late chance really for experts to cluster around this standard development organization and proactively collaborate in development of codes and standards necessary for the commercial fusion. And I will end with that, and thank you.
Brilliant. Thank you very much, Mumtaz. That's really interesting. That provided a really good overview. I think for me, what really stood out was the standards development organizations offer an excellent platform. I think that's something that we more and more see. I think it's that symbiotic relationship. We are not the experts, but we convene the technical experts who can work from those first principles and have that operational experience. And for us, we can then capture and codify that best practice. Obviously, referring back to Isabel's comments, when you standardize and ensure that at this stage it's complementary and not too prescriptive, obviously is sort of key. But yeah, really, really useful. I'd now like to hand over to Amanda Needfield, Head of Business Development at DigiLab. Over to you, Amanda.
Right, thank you very much, Seb. Thanks, everyone. It's great to be here today, and thank you, Mumtaz and Isabel, for the great introduction to Fusion and standards. I'm going to take us in a slightly different direction, but bring us back to Fusion as well. There we go. Okay, I think one slide went missing, so that's very good. So today I'm just going to talk about standards and the adoption of trustworthy AI. I want to take us through first thinking about what is trustworthy AI, where are we at with standards and AI, and how Fusion and AI standards can be really mutually beneficial in driving each other and driving innovation forward. I think there's a lot of opportunity here for the two fields. As both our speakers have already alluded to, standards are essential for commercialization and spread, and Fusion and AI are in very similar positions in their level of commercialization, specifically if we think of AI and the adoption in safety critical sectors. So just quickly, for those of you who may be new to DigiLab, I think many who came here today for Fusion will know us and our brilliant Fusion team engaging in this space. But at DigiLab, we are experts in trustworthy, explainable AI. Our tagline is "When Uncertainty Matters," and we are experts in uncertainty quantification, which is really how much confidence do you have in your model, and how much, and then you can think about where to apply it. So we are really passionate about how can we take AI and innovation and apply it to and derive value in a range of safety critical sectors. So we work in many sectors, which you can see below, including Fusion. And so we're going to talk about this today. And from the experience we have here, you can really see how Fusion can really leverage its position in the emerging regulated and emerging standardized area to adopt AI and set standards for how we can adopt AI in other safety critical sectors where there may be have more barriers to overcome to integrate it into very known and cemented processes, I might say. Let's start off talking about trustworthy AI. And trust is really essential to AI adoption. Recent ISO reports has alluded to this topic. So you can see the quote there, that leading industry experts believe that ensuring trustworthiness from the outset is one of the essential aspects to adopting AI. And trustworthiness can have a bit of subjective feel to it, but it's a very essential framework for human adoption, particularly when there's a risk and concern. And it's emerged as an essential framework for adopting AI. So I'd like to go through a little bit of a thought exercise. We think about and get a feel for what we mean of, do we trust AI? And I think a good question to follow up on that is, to do what? What is the use case to trust AI? So if we just think through a few examples. One, online shopping. So we're all interacting with AI by choice or by default in the devices and the way we operate in the world today. So if I'm shopping online, if I want to buy a pair of pants, if I want to find a recipe, or choose something to watch on YouTube or Netflix, I'm going to be interacting with AI. It's going to make suggestions. It may be more accurate or not, but it doesn't really matter if I find the pair of shoes I want to buy, or if I find the right show for my Friday evening. It can be helpful, but there's not a lot of risk or essential there. Now, if I use an LLM, you can choose the one of your preference. And I'm searching some trivia for my pub quiz. Okay, so it's not that, it doesn't matter that much if it's accurate or if I trust it. If I start to use it as an aid for my job, I want to write emails, I want to draft some answers for a tender or grant or applications I receive, then as a professional, I might start to have concerns about my trust in the answer. It might help me, but I want to check what it says. I want to take a starting point and then change where I go and adapt it to use it as a useful tool. So I can start to see that my trust in AI, in the answers it's giving me, is starting to wane, and my skepticism is starting to go up. Now, if I start to think about using AI to design a test facility, a fusion reactor, help run my electricity system, you can see that I would suggest and hope many in the audience would agree that my trust in just taking up an answer that it gives me and moving on is very low. And so the question we have when we think about standards and the adoption of AI is, what is it for, and how do we build frameworks of trust around AI? What are those elements that we can control or think about to start to give us trust and adopt these systems where the uncertainty is higher, where the risk is higher? And that illustrates how use cases really impact what does trust look like. We will have, across the three use cases we just discussed, we'll have different elements we want to consider about what equates trust in an AI application and our ability to adopt it. Another one aspect, a key aspect of trust is the method selection. AI is a broad field. There are a wide range of approaches. They all have advantages and disadvantages. So I have an illustration here to show one example of fitting a model to data. And you can see a range of approaches, and some fit better than others. Some have greater uncertainty. Some you can clearly see aren't a good fit. This is just some dummy data, so don't read too much into the exact description there. But what it quickly illustrates is that there are different methods and different approaches that are appropriate for different problems. And this is another factor we need to think about in trustworthiness. And we can see also in the method selection the level of uncertainty. So if you see the blue area on the different models, it's where the model is uncertain in its answer. And we want to know and have the visibility. So there's another aspect of AI, the explainability, the transparency of how a model made a decision, and how confident we can be in using it for its accuracy. And these all start to add up to elements that help us create and build trust in an AI approach or reduce our willingness and our ability to trust it. According to a recent MIT study, we can create a really nice model. We can understand the methods, we can feel it's appropriate for our use case, but that is just a small part, actually, of technically adopting AI. Most AI pilots, according to MIT study, only 5% are actually adopted and have some kind of impact or return. They're, in other words, able to be commercialized and used. 95% of AI pilots or exploratory areas, the proof of concepts, are set aside on a shelf. Here's something that a way to visualize this is kind of the AI adoption iceberg. So once we've built a good workflow, we have a use case, we have a method, we're very happy that it gives us an answer that we trust. There's a wide range of other considerations of how we can adopt this for a wider commercialization, the reproducibility of it. So if I want to adopt an AI solution for a nuclear fusion reactor, I need it to be verified, I need to be reproducible, I need to have it in international different operating environments. And this also opens factors of security, secure deployments, especially data sovereignty. So is my data secure? Can I have it been trained on data I can use? And then there's really essential, when talking about safety critical sectors, the cultural and sector alignments. And that's where collaborations and the efforts that BSI are leading around thinking about how does AI fit into fusion are really essential for getting the alignment. So we start to get a picture that trust in AI is a complex area. There are many factors, and it is very sector and even application specific. So we start to think about AI standards and what is the state of AI standards. So very much like fusion, it's an emerging space. There are hundreds of standards and technical specifications out there, and some apply and can be useful in some areas, and some are not relevant depending on your methods, the sector you're looking at. So we have a range of bodies and entities when we start to think about fusion and where we will adopt AI and what standards it needs to fit in. So it's one thing about AI itself, and then its sector context that needs to be considered. Trustworthiness is emerging as a key area and framework to look at. And so here I have ISO SC42 framework. There are other emerging frameworks. So if you just the ISO one, which it's a very helpful graphic, I think, to help us get understanding of the complexity of the space we're operating. IEEE has also recently issued the Standards Association Joint Specification V1 for the assessment of trustworthiness in AI systems. So we think about AI and standards and adoption. We need to ensure trustworthiness, and for that we need to adopt a framework, and that makes it agile. So adopting AI it's not something we're going to say, here's a standard for AI, but we're going to need to operate in the framework of adoption. What is the use case? What is the sector? And how does it apply? So this is a useful framework to start thinking about how we adopt and develop these standards in this emerging context, to see what illustrates trustworthiness. When we look at standards of trustworthiness, we've thought through a few of them in the previous slides. So some key ISO factors of trustworthiness are here, and they are echoed by everyone who's thinking about trustworthiness in AI. Looking at transparency and explainability. So how did a model, particularly in the safety critical sectors, how did the model come to its conclusion? How does it get its answer? How controllable and reproducible is it? Can we rely on this to give us answers consistently within the range and in the context we expect it? Is it available and resilient? So can we transport it? Is the data able to travel? If it's trained in one area, can it be used in another, and how far? How far can we extrapolate, or how much does data sovereignty allow us to carry that to international settings beyond our own borders? And then is it safe, secure, and private? There's lessons to leverage from all sorts of fields for this, but security and safety is paramount to our data and therefore our AI, our ability to adopt AI. So where does this leave this with Fusion, and Fusion driving innovation and AI adoption? So Fusion is in a very exciting space, has a great opportunity to drive the setting of standards, of course in Fusion, but I argue also in AI and AI adoption, and give solid examples to other sectors like fission and energy operations, engineering design, of how do we start to build these tools, accept them, and leverage them. And this is mutually beneficial for Fusion, as AI can help solve some core challenges across the life cycle. AI has broad applications in Fusion, from leveraging large language models, data scraping and data infiltrating for materials research, to using probabilistic methods for optimizing simulations, engineering design, control aspects, and operations. There's a whole life cycle and a whole range of applications that Fusion can drive the exploration and adoption of AI and help set the standards. And it has a window, not yet commercialized, that it can do this in a front-footed way, where other sectors will, from a regulatory perspective, take a slower, as they should, a slower approach. But similarly, the workforce, the tools that are used, the fusionics of the future have the opportunity to have AI and machine learning in their toolbox from day one. And this is a really exciting prospect. So Fusion can lead on the adoption of AI, but also I think AI can help solve some challenges in Fusion, but also it can help maybe set standards that are different challenges. So one quite known example is about tritium accountancy. Traditional methods have a hard time if we go from a frequentist approach to tritium accountancy. So this is in your fusion reactor. Tritium is a key part of the fuel cycle, and it will proliferate across the machine. We need to know where it is as a radioactive material. AI, and taking a probabilistic approach, can help solve this challenge and inform standards for how we manage tritium accountancy and other nuclear standards and regulations as well. So a real mutually beneficial area where we can start to leverage these two technologies, their emerging state of commercialization, and how we can drive innovation in realizing our energy future. So thank you very much for your attention. I think I hand it back to Seb, and I look forward to the discussion.
Brilliant. Thank you so much, Amanda. You probably want to keep your camera on there, because I'll invite anyone to turn their camera on. But yeah, really, really interesting. I hadn't thought of AI informing standards or how that works. The other thing that is sort of really interesting is that trust in AI is so critical. I know we talk about it a lot, but as you were talking, it becomes more, as AI might become more intelligent than humans, and we are potentially deploying this in safety critical domains. That's the public trust element there, which, so how do you communicate that? So trust in AI is so critical in these areas. So yeah, thank you very much for that. So thank you all for very insightful perspectives there. And particularly on how you think standardization can contribute to the deployment of fusion technology to meet clean energy power objectives by 2030. So I'm keen to sort of do a little bit of a deeper dive and have a discussion. We have got a clock ticking. We might go over by 1 or 2 minutes, so that clock won't cut off, I've been assured, which is nice to know. So that takes the stress of me for a little bit. But yeah, I'm keen to sort of ask you guys a few questions. Also for the audience, please do participate and ask any questions, and we'll try and put them to the panel. Firstly, I mean, one of the questions that came up from your perspective, Isabel, what are some of the most immediate challenges in applying standards to fusion projects? And you mentioned sort of not being too prescriptive. How can they be addressed without necessarily stifling innovation?
So I think that's a really important question, because we know from all of our enterprises as humans that we learn by doing. And it's only by doing things that we really start to understand what is important and what needs to be standardized. So, thinking about the UK civil nuclear program, for example, we've learned a huge amount from that over the years. And what we absolutely don't want to do is close down an avenue of investigation. So for me at the moment, it is about recognizing that fusion as a technology is still very immature. No one has demonstrated commercial fusion power yet. We're working towards it, and standardization will enable that commercial demonstration. But the standards that we should be focusing on for those initial enabling demonstrations are the standards that to some extent we already have, standards around rebar or screw threads. And what we need to do is share what we're learning across the fusion industry and collaborate, because it's only by sharing that information that we will accelerate our understanding of those technologies, and in doing so, really understand what we need to standardize. Oh, Seb, you're on mute.
Thank you. Only been doing this for 5 years, right? It is interesting, and I think there's a couple of sort of observations there. We did something in carbon capture and storage where we looked at the existing standards for oil and gas, saying actually where have we got existing standards that you can apply already? And I think that there's a few thoughts that we should have, and one of those is the least amount of standards is probably the best outcome, right? Because more proliferation isn't necessarily the best thing. And so there is an element of saying if you want to commercialize, standardization helps with that, and you sort of sketch that out, but there is a sort of right time and potentially a wrong time to sort of standardize. And also making sure that you set out, as you mentioned, from a not too prescriptive way to start with, because again, you could stifle innovation sort of that way. But again, they do have a massive application in sort of exporting that and really providing that baseline for innovation and a platform that you can build upon. Mutaz or Amanda, did you guys have any sort of thoughts on that specifically?
If I may, I would certainly second that, in recognition of that most of the programs, fusion programs currently are looking to develop prototype reactors. And I think, the non-restrictive approach is definitely very enabling and is very much in alignment with the current phase where fusion the technology is at the minute. Perhaps the prescriptive aspect of it would be a follow-on step after the next generation of prototypes, but definitely at this stage it doesn't need to be restrictive. So I'd agree with that.
Brilliant. Did you have any thoughts, Amanda? Don't worry if not. But
not on that one. Thank you.
I've got a question mainly from a UK AEA point of view. I know the UK AEA is working to ensure fusion delivers both scientific and economic value, which is obviously a very big driver currently politically, economic growth, green growth. How do you see standards playing a role in accelerating that mission?
I would say a very critical role indeed. As I say, especially that fusion now is it's taking very fast pace to transition from fundamental research to commercialization, and standards, of course, does provide an acceptable and shared framework needed to bridge this gap. And just to give few examples, which has been mentioned, is data and knowledge transfer. This is really open science to commercial IPs. and it reduces time to market for commercial fusion plants. It also leads to development of supply chain, and with the advantage of aiming for harmonized international standards, this will also allow the UK to compete in a global market. And of course, also standards will ensure quality, reliability, and cost reduction, and most importantly, really de-risking the commercialization of the fusion as a whole, which is an important signal to boost investment into the sector.
Yes, and de-risking is obviously a great sort of example there. Did anyone else have any sort of thoughts on that and any observations? Did I see a hand move there?
Yeah, no, I was just going to come in and say, in terms of the economic value, I think I'd also add around social value. Standards give us a way of explaining to people what we're trying to do and why, and that confidence in understanding of what we're doing and why helps us to identify the skills that we're going to need as a nation to deliver this, and being clear on what those skills are helps education providers set up the right training programs, and in doing so deliver that social value in terms of jobs for communities across the UK.
Yeah, that's really interesting. And everywhere, you know, all the sort of councils and advisory groups that I sit on, they all talk about the sort of skills gap and how, you know, that's one is sort of actually the R&D, and we can do all of that. But actually, do we have the necessary skills to deliver this? And I think the broad consensus in most areas, if you look at the energy transition, whichever area you look at, you know, I think nearly every area recognises that there is a sort of skills gap. And so, yeah, that's a really good point. And yeah, the social value also links into that sort of public perception, even with something as safe as sort of fusion, that there is, with nuclear, there is always this sort of public element that you always have to sort of consider about. I've got a friend who deals in nuclear waste, and when we go out for drinks, he always talks to me about it. And it's a very, very important area which we sometimes overlook. Probably want to sort of just jump back to AI. It was a great presentation, Amanda. And obviously you sort of lined out that it is being used in the fusion sector, particularly for elements like control, diagnostics, and safety. Are there any unique challenges that you see that arise when applying standards for AI in such a safety critical environment, and anything that we really need to be aware of?
Yeah, certainly. I think there's the trust and the awareness and the education, and going back to the point that Isabel was just talking about skills and awareness, to have whole teams who are engaging with this understand AI, where it fits in, where the risks are, and in most safety critical areas, it's most appropriate to have a human in the loop solution so that we can leverage the tools of AI. And mostly in these sectors, we're going to be focusing on machine learning, but also have that check at the appropriate times for the appropriate application to do that. So accounting for that, and underneath that is the kind of the tension between having a standard that sets out in a more traditional software thinking approach how something should be done in a deterministic way, and the sort of probabilistic changing nature of AI applications. There will be situations where we deploy a model and it does the one thing it's trained to do, but in most situations, for example, like the control room, you want to update that with your learning. You want that constantly to be evolving. So the challenges of developing standards that are flexible enough to account for that, but also restricted enough to give us a standardized approach, and that security and safety are really essential. So balancing that line and finding how to do that with this emerging tech, I think, is essential.
Yeah, and I think maybe some of those standards, I think the thing that I always look at is that they are best practice at a point in time, particularly in innovative areas, right? Like things will change, and having a baseline that might not be perfect but good. You know, the tricky part is we're doing that in safety critical areas, which sort of brings a whole lot of other sort of questions to that. But you know, that there is a sort of baseline that we can iterate from, which I think we sometimes forget really. And yeah, I think there's an interplay there as well with standards and how they can support regulation, because there's a lot of sort of questions there. Yeah, sorry, go on.
Oh, sorry. No, I think understanding particular techniques and aspects of models that we can standardize or use across them to give visibility to what they're doing. That's the transparency and explainability is where standards can really have a role in making that baseline approach of understanding what's happening.
Yes. We also have some audience questions that have come in, some of which I'm completely ill-equipped to answer, so it's always great. This one seems to be one for you, maybe Matthias, or for you, Isabel. Why can we not store the energy of heat from the heated plasma in some material which can stay heated for a long time? This way, it creates electrical potential by heat and provides energy by potentially powering homes. Any thoughts on that?
I mean, it's definitely a very, very brilliant concept, indeed. I think a lot of the fusion concepts have not considered yet anything beyond the fusion machine, and I think the term for it, they call it balance of plant, which is almost considered as a standard type of system, but no, yeah, it's a brilliant idea. I think it's something that should be considered in terms of material development as well.
Yeah, I think you've disappeared from the camera view. We can only see your background, but yeah, it's an interesting one. And I suppose there's so much technical complexity with this as it is that you probably don't want to think about the sort of adjacent applications at this stage when it's still very much a nascent technology. Is that correct?
Yes, that's right. Yes.
Yeah. There's a question here which I can probably answer, but keen to see if anyone else has any sort of views on that. Has leaving the EU rather complicated getting international agreements on standards, etc.? I can give the sort of BSI standards answer there is post-Brexit, we remained members of CEN and CENELEC, the European standards bodies. We are still, we are members of ISO, but we're also members of CEN and CENELEC, and that was continued after Brexit. So from that point of view, from a standardization point of view, from where we're sitting, no, we still represent the UK at all those international standards fora. So from that point of view, no, but I don't know if there's any sort of counter view from those on the technical committees. Isabel, I see you've unmuted there.
Yeah, I just echo what you said. The work that we've been doing within the NC 1, 2 and 3 committees in particular, we've been working with colleagues outside of the EU as well, Canada, China, Japan. So from that point of view, nothing's changed, and I know that we're still working really closely, for example, with the German national standards body, particularly around fusion. So I'd say that we're still working really well together. Yeah,
and we're working very well with our counterparts as well, including DIN on a number of areas, which is the German sort of standards body. It's great to see that point was reinforced. I just had a slight flutter to go. so that's great. We've also got a question from Lara Jameson, who says, thank you for the interesting talks. How do you see the interaction of experiments and simulation and AI in fusion regulation? Amanda, I don't know if you can answer that very easy sort of question, but I think AI and regulation and standards is a difficult sort of area as it is. So apply to something like fusion is an interesting one. I don't know if you have any views on that.
I think I shared many, I think, in my talk. I think the interplay is very complex. I think the thinking in a sector-specific, domain-specific approach to AI and creating AI standards for the sector, but specifically in safety critical areas where the domain is quite specific, constrained, and particular to that is probably the most fruitful approach. You can't solve everything with one approach. So.
No, and I do think standards, I think one of the things that I sort of often advocate for is that I think standards play a role in supporting regulation. Standards have a certain timelines associated with it, right? Not always the sort of fastest, but there's a due process with that. And I think standards can really support regulators and regulation, because in, you know, completely different area in energy, regulation was always struggling to sort of keep up with some of the change. And I think that there's a role for standards there, particularly when in some of the areas where we're looking at this good practice here that you can sort of point to from a regulatory point of view. So it definitely is a sort of very close interplay there.
Going back to the EU question, leaving the EU has changed regulation for AI in the UK and taken us in a different direction where we have different options in this environment. So standards play a role in building the trust where that regulation may not be in place.
Mutas, I see you've unmuted there as well. Do you want to come in on that point?
Yes, absolutely. I think with the probabilistic approach and regulation, obviously the nuclear fission have been implementing probabilistic approaches for plants that are already in service, and the regulators have been monitoring this closely, and I think with some time this will be adopted, albeit is going to be for plants already in service. Obviously, the biggest challenge is to being able to adopt these probabilistic approaches and AI as well at the early on stages where you're designing with limited available data. So yeah, so there is already some precedence in terms of implementation of probabilistic approaches in safety critical situations, but there are still challenges to be overcome.
Yes, no, thank you very much for that. I am acutely aware of time, and I should be rounding up now. As I say, we've got a clock tick, and we can go over 1 or 2 minutes. I want to sort of nearly end it there, but there's one question that we have that I did want to pose to you, Isabel, and potentially to a wider panel before we go. But from your perspective, what role should government ambition and policy play in supporting or even mandating the use of standards for fusion, and what recommendation would you give to policymakers? I think for me that's a really interesting question from the point of view that I always see that standards play that role in helping to deliver on some of that policy ambition. I think there's also more of a broader thing. If we are wanting to be a leader in this case in fusion, what's the role that standards play, and what's our role as the national standards body? So I thought I'll conclude on that sort of question, and anyone please jump in. That would be the final question, and then I'll
so I think there's a great big opportunity here for us in the UK to take the lead in determining what those standards are going to be. So what I would say to policymakers is be really clear about what it is that we're trying to achieve with fusion, and be really clear that we want to collaborate. We don't want to work on this alone. We want to create this unified, this consistent approach, which means that we can share learning and we can share supply chains internationally, because we recognize that we have different expertise in different countries in terms of supply chain, manufacturing, etc. It's got to be a collaborative effort. We see that at ITER. So being really clear as policymakers with other international policymakers that we're out to collaborate, not to compete. That's the most important thing.
That's fantastic. Thank you very much. Did anyone else have any other sort of thoughts on that? Looking for the virtual eye contact. Then we've not Mutas. There you are. Yeah.
Yes, and I think this is really sort of the setting stone for allowing the next step of technical collaborations, because once you've got this multilateral recognition, then it allows multilateral exchange of all the technical pieces that are being developed by any technical committee or working group, wherever they are, which is again open global collaborations at a technical level, which has huge benefits in terms of technical expertise, time, and cost as well.
Fantastic. No, thank you very much. So I think we're up for time. I've got to say it's terrible hosting by myself because we're just slightly over. But I want to thank you, the panelists, for sharing your expertise with us today. I want to thank you, the audience, for your thoughtful questions. There's a few that we've missed. We'll see if we can sort of address those in a sort of follow-up. I think it's been a really incredibly rich discussion, really highlighting the importance of standards and standardization in providing, hopefully, an enabling framework to scale up nuclear fusion at pace. I do feel this is just the beginning. There's a lot of momentum and opportunity for fusion energy, and From the direction set out by the Nuclear Regulatory Task Force recent report, is clear that regulation must become more agile, proportionate, and sort of forward-looking. So the call really is a reset of the regulatory system, and there's a role that standards play to support that and providing that enabling framework for innovation. So thank you again for your time and participation. If you in the audience are interested in continuing this discussion or learning more, I think we mentioned a link, but we would also like to hear from you, so feel free to connect. And if there's anything more that you want, just email us, because we're very keen on continuing that. Probably a couple of things to highlight. We've got Net Zero Week, as I mentioned at the start. It's a week of webinars, so on the following days you can see these different webinars. And there's another slide as well. Next slide, please, if I'm not mistaken. Yes, there's a digital conference as well for Design and Build in Fusion on the 14th and 15th of October this year. So we can send out a link to that. But if you are interested in Fusion, this is one of those very good conferences to go to, and you can attend it from the comfort of your own home. So please do visit this. We will put all of this in follow-up email with links. Once again, to the panel, thank you very much, and thank you very much to the audience.
Thank you.
Thank you very much.
Cheers.